We're back with another session on the IC 555 tutorial, and in this session we're going to cover its internal schematic and how the IC 555 works and operates. As you know, the IC 555 is one of those ICs that's mostly said to be made for hobby circuits, but honestly we can do a lot of other things with it too. But if we want to go over the IC 555, we should position it so that this notch at the top is facing us. Sometimes there might also be a small circle on the top left corner, and this way we can identify the pins here. Pin 1 is ground, pin 2 is the trigger, pin 3 is the output, pin 4 is reset, pin 5 is for voltage control, pin 6 is the threshold pin, pin 7 handles the discharge process, and pin 8 is connected to the power supply, or VCC. This is also the schematic that we use for the IC 555 in various software, or if we want to draw a circuit, its schematic looks like this. Unlike the way it's shown in this diagram, where the pins are, for example, on the left, 1, 2, 3, 4, 5, up to pin 8, we don't display it like that. Instead, if you look, this is the actual schematic of the IC 555, and the pins are arranged like this. For example, this is pin 1 here, pin 2, then pin 3 is actually on this side, and so on. This is a schematic of the IC 555, and as we mentioned, when we want to draw it in software and use the different pins, this is the general layout of this IC. But if we want to generally see what the inside of an IC looks like, as you can see, this is a diagram of the inside of the IC 555, which is shown to us in a simplified way. But it's not exactly like this either. For example, inside these comparators, which are shown here as triangles, there are actually other electronic components inside them. The same goes for the flip-flop, and it's much more complex, but we don't really deal with those details. And this is another detailed perspective of the integrated circuit, which, based specifically on the complex schematic output you typically get in the design software, you can actually design it exactly like this for your project. But generally speaking, if I want to explain it so it's easier to understand, the schematic inside the 55 IC looks like this. You can see here that we have two comparators, which we call comparators. As we mentioned, this is the flip-flop. Then we have an inverter here, and after that we have two transistors in this section that we use, and there's a voltage divider. Here, look at this section. Generally, it's called a voltage divider, which consists of three 5 kilo ohm resistors. Some people even believe that the reason it's called the IC 555 or 555 IC is because of these three resistors, each of which is 5 kilo ohms. That's why they say it was named that way, although maybe that's just one of the reasons. Alright, now let's move on to this schematic and go through it step by step to see what it does. As we said, this part is the voltage divider. Let me highlight this section. This is the same voltage divider that's connected to the power supply, meaning this VCC terminal. I'll tell you in a bit what voltage range it should be in, but it's connected to the power and this pin here. And well, as we said, this is a voltage divider circuit that divides the supply voltage, and once it does that, these two voltage comparators draw their power from it and do their job. Well, since all the resistors are identical, the supply voltage, or VCC, along with the input of comparator 1, which I'm showing here, ends up taking 2/3 of the supply voltage. We'll get more familiar with this part as we go on, and the second comparator takes 1/3 for itself. Now, the range of VCC that we use for our 555 IC is generally a supply voltage between 4.5 and 16 volts, but we can consider 5 to 15 volts as a sort of safe range. For example, I'm saying they said it can work from 4.5 to 16 volts, but for safety, we consider 5 to 15 volts. Let's assume our circuit is running on a 9-volt battery. So according to what I just said, the first comparator, which we'll call C1, takes 2/3 of the voltage, which here is 6 volts, and you can see that's also its negative input. Look, if you pay attention to this part, the negative input of comparator 1 is set to 6 volts. That means it takes 2/3 of this input voltage for itself. Whereas in the second comparator circuit, the positive input terminal has taken exactly 1/3 of the total voltage for itself. And in this specific part, if you take a close look at comparator number 1, you will see that the positive input here is directly connected to pin 6. In this demonstration, I am showing that the non-inverting positive input of the first comparator is directly connected to pin 6, whereas for the second comparator in the circuit, its inverting negative input is connected to pin 2 of our integrated circuit chip. So here, we can have this output up to this point. If we connect a 9-volt battery, according to the programming that this 555 IC itself has, this part, the voltage for the first comparator, receives 2/3 of the voltage, and the second comparator receives 1/3 of the voltage. Initially, the negative input of the first comparator, which gets 2/3 of the voltage, is at 6 volts. And the positive input of this first comparator is connected to the output at pin 6, which is our threshold pin. And for the second comparator, its positive input has 3 volts, which is 1/3 of the VCC voltage, and the negative input, which here belongs to the second comparator, is connected to our pin 2, which is the trigger pin. Now, what are these comparators? Comparators are devices that compare voltages. At their inputs and outputs, they produce a digital signal that indicates which of the inputs is greater. If our positive input is greater, which as shown here in the diagram we denote with V1, if the positive input is greater than the negative input, then our output will be in the high state. Now, if our negative input happens to be significantly larger than our positive input, then in this particular case, our resulting output will be held in the logic low state. Now, let's go back to this part again. Here, let's take a look at comparator 1. Let's have you take a look. In this specific configuration, the positive non-inverting input of this first comparator is directly connected to pin number 6. Meanwhile, the negative inverting input is being divided by the 9-volt VCC supply, which effectively gives it exactly 2/3 of that total voltage, resulting in a steady 6 volts. And right here, we can clearly see that the negative input voltage is currently higher than the positive input voltage. Consequently, the resulting output of this particular comparator is held in the low state. Now, if we increase the voltage at our pin 6, for example, even if it's just 1 volt more, or even half a volt more, look here, if I set it to 7 volts, if the voltage at our pin 6 is greater than the 6 volts, we see that V1 becomes greater than V2, and the comparator shows us a high output. Now, if our pin 6 drops below 6 volts again, meaning, for example, in this part, it becomes 0 volts, as I'm showing here, if it becomes 0 volts here, then our negative input becomes greater than this part again, and the output of our comparator returns to the low state. Now let's take a look at the second comparator to see how it works. Now in the second comparator, our positive input, which is connected to the voltage divider, receives 1/3 of VCC. So with our VCC at 9 volts, we have 3 volts, and the negative input, which is 0, is connected to pin 2, or the trigger. Now, if the voltage at pin 2, here at pin 2, is less than these 3 volts, as you can see in the image, our output will be in the high state. Now, if the voltage at pin 2 happens to rise above the 3 volt threshold, which in this specific example I have shown as being 6 volts, and the actual input signal at pin 2 becomes significantly greater than the positive reference input of the second comparator, the resulting output that we get here will begin to decrease rapidly and will eventually transition into the fully low state. You can think of this low and high as 0 and 1. Let's say high is 1, or for example on, and 0 is low or off. That way you can simplify it for yourself. That's right. Now, as soon as our pin 2 drops below 3 volts again, any value below 3 volts, all the way down to 0 volts, our project will switch back to the high state. So where are these comparator outputs actually useful? The output from these comparators goes to 2 inputs of a flip-flop, and that's where a series of operations takes place. Look, here we have a flip-flop. It's this rectangle in the middle, and on the left side, those are the outputs from the comparators, which can be in either a high or low state. These connect to the set and reset pins, which we label as S and R, and they're shown here on the flip-flop. But before we continue further with our detailed discussion today, let me take a moment to give you a very brief and clear explanation about exactly how these flip-flops work in a circuit. A flip-flop has 2 inputs, set and reset, which, as I mentioned, are represented by the letters S and R. Then it has 2 outputs, Q and not Q, and we show not Q like this. So it has 2 outputs, Q and not Q. For now, don't pay too much attention to the low and high written here. This not Q is always the inverse of Q. Now, when S, or set, is in the high state, our Q output is high, while not Q, as you can see, is the inverse. Now, if both of our inputs are in the low state, are low, look, in the previous state, our reset pin was low, and when our S, or set, is high, this is the output we have, meaning Q is high and not Q, which is the opposite of Q. Now, when both set and reset are in the low state, you see the output doesn't change compared to this diagram. So we're comparing these two right now. That means if both of these are low, our output will be high and low. If our set is high and our reset is low, again, our output will be set like this. Now, when our reset input, or R, is set to a high state, and our set input remains at a low level, our output Q will consequently transition to a low state as well. But the not Q output, which we previously mentioned is always the logical inverse of Q, will instead be driven to a high state. Now, one point to note here is that while our flip-flops generally have 2 outputs, Q and not Q, in the 555 IC, we only consider the not Q output. That means the Q output is not used for us, and we use this one instead. So in the 555 IC, what matters to us is the one that appears at the not Q output. Now, let's bring together all those comparators and flip-flops here, and keep your eyes on the table on the right side of this section, because we're going to proceed according to that. Look, when our VCC input is at 9 volts, it means we've still connected a 9-volt battery to this. Our pin 6 here is in a low state, meaning it's at 0 volts. Look, according to this table, if pin 6 is low and the negative output of our comparator is 6 volts, and what it gives us, based on what we discussed earlier, you can go back and check, the output of our first comparator is in a low state. And our pin 2 here, when it's also in a low state, meaning it's less than 3 volts, as we mentioned before, the output of our second comparator will be in a high state. All right, now look here. In this flip-flop, the R and S are shown like this in the 505 IC. In the 555 IC, you need to pay attention to which one is R and which one is S. Now, in the 555 IC, S is connected to comparator 2, and R is connected to comparator 1. Based on the information we see here, our R input is currently in the logic low state, while S is in the logic high state, and the complementary output, not Q, is also in the logic low state. Look, here, according to this diagram, first R is low, S is high, not Q is in the low state, and as we said, we don't deal with Q anymore. We only work with not Q. Now, if we proceed like this, pin 2 generally acts as a starter, which starts the timer for us and also sets the flip-flop right after that. Of course, if we want to have more than one timer tick, for example, to have that electronic eye, our flip-flop needs to be reset. Here, according to this diagram, our pin 2 is in a state where its voltage is higher compared to this 3 volts, so it is in a low state. And our comparator 1 is just like before. Nothing has changed. This V1 is greater than V2 and is in a low state. And now both the R and S pins are in a low state. And again, our output, meaning our not Q, is in a low state. Now, as we said, when we want to have more than one timer tick, the flip-flop needs to be reset. How do we do this? First, the voltage at pin 2 needs to go above 3 volts, which in this case, our pin 2 is at 9 volts. All right, after that, when our pin 6, look, here we said that our pin 2 goes above 9 volts, so it goes into the low state. Now, when our pin 6 goes above 6 volts, our output goes into the high state, which causes the flip-flop to reset and our not Q output to go high. So if we take a close look at this diagram right here, let me just go back for a moment so we can really take a look. If our second output is currently sitting at 9 volts and our output 6, or perhaps it is better to say pin 6, is in the low state, then the final output we get from the flip-flop is also in the low state. And we previously said that if we want the specific tick timer action to happen more than just once, meaning that the 0 and 1 states keep alternating back and forth and we keep getting that continuous output, then our pin 6 also needs to have a voltage level that is significantly higher than the 6 volt level at comparator 1. This is necessary so that we can properly reset this pin and have it cycle all the way back to repeat the entire process over again. Here, you can clearly see that in this particular part of the circuit, our pin 2 is at 9 volts and comparator number 2 is completely and fully in the low state. When our pin 6 sees a voltage of 9 volts, comparator C1 goes into the high state. And when R is high and S is low, not Q is in the high state, according to the table shown here. And now, as for why pin 6 has reached 9 volts, well, that depends on the circuit we set up and where the voltage is applied. But generally, with the 555 IC, even in the process we followed so far, we saw that we would connect pin 2 to pin 6, and these pins share these voltages and become connected to each other. So in this way, we can reset this pin, meaning we reset this flip-flop, and the not Q output here goes high. The point here is that in a flip-flop, we never want both inputs to be high at the same time, meaning both the S and R inputs are high. What happens when this occurs? When both of our outputs are in the high state, look, right now our comparator, meaning if I disconnect the voltage from pin 2, that is, set it to 0 volts, the comparator goes high. And our pin 6, which has 9 volts, compared to this negative pin, the comparator's voltage is higher, or in the high state. This means both R and S are in the high state, and as we said about flip-flops, we never want these two to be high at the same time. Why? Because if both of these are high at the same time, our not Q output will show us an unpredictable output, or in other words, it will be invalid. So we never want pin 6 to be high, or in other words, in the high state, while pin 2 is in the low state, because this would cause both comparators to simultaneously show a high output. And ultimately, the output that the flip-flop gives us would be invalid. You can see this in the table as well. You can observe that in this table, If both are in the high state, the output of our flip-flop will ultimately be invalid, and the circuit won't give us any output. That means when this is invalid, obviously whatever comes out of here isn't something we can, for example, display with an LED. Or it might be displayed, but it won't give us what we want. We need to pay attention to the fact that pin 2 should never be in the low state while pin 6 is in the high state. In other words, they must always be connected at the same time. So right now, the flip-flop pins are giving us a digital signal, either low or high, and this is sent to the output pin of the 555 timer. What is the output of the 555 fiber? It's this pin 3 that we see here. So first, the signal comes from an inverter that's here and is also connected to the flip-flop. It passes through this, and then it reaches pin 3, which is the effective output that comes from this NOT Q. This shows us the path of the signal from input to output in this way, and covers it. But now, we still have 3 other pins that we need to talk about. Here, we have pin 5. Pin 5 is related to the 555 IC, which controls the voltage. If you look closely, it's also connected to the negative input of comparator 1, which usually has a voltage equal to 2/3 of the voltage we're using. But we can also utilize the 5th pin of the integrated circuit for the purpose of setting or fine-tuning specific parameters, or alternatively, use it to precisely regulate the output voltage levels. So that's pin 5, which you can see is connected to this pin. So we can use pin 5, which is the voltage control pin, to control and adjust the voltage. In some cases, to reset the circuit more easily, we can have an ideal solution. What is that solution? If we want to reset the circuit, as shown here, you can see that pin 4 is connected to the base of the transistor, and this transistor needs to be in the on state for our 555 IC to work. Therefore, pin 4 is usually connected to VCC. That means, using a jumper wire, we connect pin 4 to pin 8. Why do I say it's connected to VCC? Pin 8 is our VCC. So we usually use a jumper wire to connect pin 4 to pin 8, so it can always keep it in the high state. Now, if you consider that pin 4 is always connected directly to the ground and consistently stays in a low voltage state, then our internal transistor will effectively turn off. This specific action causes the internal triggers to reset completely, which ultimately results in our 555 timer output signal dropping down to a low state. The last pin we want to look at here is pin number 7, which is the discharge pin and is used with external capacitors. That means capacitors are connected to this pin, and when we want to measure time intervals using the 555 IC, we use pin 7 for that purpose. Now here, I've shown a schematic where, for example, this is a capacitor. It's a capacitor that, as we said, pin 7 uses external capacitors. In the 555, pin 7 is connected to another transistor. As you can see in this diagram, its pin is controlled by the output of the flip-flop. Look, this is pin number 7. Right here, this is a standard transistor, and this specific part is the base pin of the transistor, which is directly connected to our flip-flop circuit at this exact point. So we say that the base pin of our transistor is controlled by the output of the flip-flop. When the output of the 555 IC is high, NOT Q goes low. So the transistor turns off. What does this cause? This causes the capacitor to start charging, and when the capacitor is charged, it triggers a reset, meaning the reset process happens again. This makes the circuit reset, the transistor turns on again, and when the transistor turns on, the capacitor discharges again. Here, I kept the red color for a bit to show that it's discharging, but in reality, it goes all the way down. At this point, the capacitor discharges, meaning it's connected to ground and allowed to fully discharge, and that's how pin 7 works. Up to this point, I've shown you the general operation of this 555 IC, like how the pins should be set up in different states so that we can get an output that's visible. For example, pins 2 and 6 can't both be in a high state at the same time, and this prevents us from getting the desired output. We also saw when the flip-flop can be reset and start the process over again, allowing us to have multiple cycles and oscillations. Here, we also saw how the outputs of pins 5, 4, and 7 behave and what process we will have. You can watch this video again, and with the diagrams shown here, you'll definitely be able to more easily follow how it works and see exactly how the 55 IC operates. But along with these explanations, we can understand this even better if we build more circuits. The more circuits we assemble, the better we'll be able to truly grasp how the IC works. In future sessions, we'll build other circuits, and in those parts, we'll also review and remind you of what we discussed in this section.